talking about logistic regression, and we're going to be considering this Titanic data set in which we have the we have the roster for the Titanic, so the name of these individuals along with if they survived or if they died. We have their passenger class, we have their age at that time, we have their gender, we have various other variables such as fare, embarked, that we can use to try and predict the survival with logistic regression. So logistic regression models response variables, y values, that are categories. The categories have to be binary, true or false. So survived or died. Okay, we're going to start by visualizing this data set. So one question you could ask is, does age affect survival on the Titanic? It's hard to tell if it is the case or it is not the case, because ideally we'd like to see some separation where the points on top here do not overlap with the points on bottom, or more precisely overlap less. That's not the case here. There's a lot of overlap, but there is some evidence for yes. So for example, if you're over 60 years old, it looks like generally you had a much higher chance of dying. Okay? If you were younger, it seems like you have a better chance of surviving if, for example, you're less than 5 years old, but it's not great. Okay. So we're going to model this with a logistic function, a sigmoid. Okay. The sigmoid function looks like this. And here, the variable z is going to be a linear combination of the input variables. This is called a bias here, but that's also called the intercept. So an intercept term b plus weights for each input variables. Okay, and so we can input this into the logistic function. Now, a very common thing to do is to investigate the log of odds in linear regression. The odds is given by this: the odds that it happens versus the odds, the probability it happens, event 1, which is generally considered the yes outcome happens, the probability of it divided by the probability it does not happen. Okay? If we take the natural logarithm, there's this relationship that you can prove that you get just this term right here. Okay? And these terms come from the regression equation. Okay? So, for example, if you look at the probability of survival by sex, you can see that women were much more likely to survive, like 74% versus like 19%. Okay. This can be reflected in the p-values, and also you can use the regression coefficients to examine not just the p-values, but also the odds ratio. Okay, so remember, the probability here is high, but let's see what the odds ratio looks like. And the odds ratio is going to be connected to the log of odds. Okay, so does the input affect the output? If we just model this with age, the answer is probably, right? The p-value here is 0.04. The null hypothesis is age does not affect survival. The p-value here is less than 5%. So most people are going to reject that age does not affect survival and conclude that age does affect survival based on this p-value. Now you can have a confidence interval for the coefficient. So the coefficient value, so that is the W1 here, W1, it's estimated to be negative 0.01, but it could be as small as minus 0.02 or as large as 0.001. Okay. Now, if we look at a regression model that just has sex, well, sex has most definitely affects the output. The p-value here is so small, we are going to call it 0. So we're going to reject that sex does not affect the output at the 1% level of significance, even the 0.1 level of significance. So we're very certain that played a role in determining survival, and conclude that sex does affect survival. Okay. Now we can look at the odds ratio. The odds, the probability event occurring divided by the probability event not occurring. So this is the odds of survival. And it has this relationship. So when we take the odds ratio, that is when it's x plus 1 versus x, we just exponentiate the weight. Okay, so the odds ratio for a male surviving compared to a female surviving is 0.08. That is, males' odds of survival is 0.08 that of women's. It's much smaller, and it's a multiplicative factor. We could look at what's called a main effects model, which would be, hey, I have two variables. Why limit myself to just using one variable? Both age and sex seem to affect it. So when we account for age, it looks like, when we account for age and sex, it looks like the thing that determines survival is not actually age, but it happened to be gender. Okay. So here, this p-value is 0.39. We'd fail to reject that age does not affect the output. So in effect, we conclude age does not affect the output based on this p-value. And we would conclude that that the variable of male or sex does affect survival. So since this variable is not significant, we would drop it out, and we just use this model that only has sex in it, and male or female here. And we would conclude that this is the model we need, and the only model we need of these two variables. Okay. Now there are more variables to explore, but of age and sex, these are the only two. And this would be the model that we choose based off of p-values. So p-values can be used to select models, and that's not something you've seen before. Okay. Now something that's really, really important is this odds ratio. So there's this interpretation of generally not the intercept, but the slope coefficients. So you can read this if you'd like, but generally it's for the slope. Okay, so if b1 is greater than 0, that means the odds of the event increase as x1 increases. And I expect you to tell me exactly how much it increases. And you have to do that in terms of the odds ratio. But this is just a conceptual thing. If beta 1 is less than 0, the odds decrease as it increases. And if it's equal to 0, there is no change in odds. That means that the input does not affect the output. Okay. So let's just go over the main model. So for the sex male is minus 2.51, and that represents the odds, the change in log odds when the passenger is male compared to female. Okay, because it's negative, we know it's lower for men. Okay, the odds of survival for males is minus 1.45. The odds ratio for males compared to females is 0.08. And this is the really important part. This is what I expect and I like to test on. is this part. Okay? This means the odds of a male surviving is about 0.08 times the odds of a female surviving on the Titanic. Okay? So you can read over and check the other models. So I do this for age. So if you had an age model, you can interpret the coefficient of age, and that's why those confidence intervals are really useful. And if you just used an age model, it would say the odds ratio for a 1 year increase is 0.98, which means that for each additional year of age, the odds of survival is multiplied by 0.98, meaning you're going down in your survival odds just slightly. Then you could do this for the main effects model with 2 variables, but again, the model that we would use here is just this one, and that choice was made off of the p-values. Okay, so I'm going to stop here because these are the main facts that you need to know: the odds ratio, interpreting the coefficients, and the p-values, okay, for variable selection. Okay, thank you very much.